Hey everyone, and welcome. We're diving into string theory today,
Oh, very cool. A deep dive. I like it.
using this really fascinating article by physicist Edward Witten. It's called What Every Physicist Should Know About String Theory.
Ah, Witten, a classic.
Yeah, so it's pretty dense stuff. We're going to try to break it down into, pieces that are easier to digest.
Right, right. Make it fun.
Exactly. Like, how does string theory try to, I don't know, like marry quantum mechanics and general relativity?
Yeah, well, that's the holy grail, isn't it? Unifying those two.
Right.
String theory basically says instead of these point-like particles, everything's actually, these tiny little vibrating strings.
Okay, so not little billiard balls, but tiny little strings. What
Yeah.
difference does that make?
Well, it's huge. These strings, they vibrate, right? Different frequencies, and those vibrations determine everything. Matter, forces, even space-time.
So, like, the universe is like a giant symphony.
Exactly. Like different notes on a guitar string. It's all about vibrations.
That's a pretty elegant way to think about it. Okay, so Witten, he talks about these rhymes in physics. What did he mean by that?
So think about waves, right? Water waves, sound waves, light waves, even gravity waves,
Hmm.
ripples in space-time.
Okay.
They seem totally different, but underneath, they share this fundamental principle, energy moving through a medium.
Okay, so like a pattern repeating in different places.
Exactly. And string theory says maybe those rhymes aren't just coincidences. Maybe the forces and particles we see, they're just different vibrations of these fundamental strings.
So it's like the spiral of a seashell is kind of like the spiral of a galaxy, like these hidden patterns.
Yeah, like there's this underlying structure to everything.
That's wild. But how can we study something as small as a string, especially if they're connected to something as massive as gravity?
Well, Witten starts by simplifying things. He looks at quantum gravity, but in just one dimension.
One dimension. So, like, the universe stripped down to the bare minimum.
Yeah. And you know what's cool? Even though it's simplified, it shows this deep connection between quantum gravity in one dimension and regular quantum field theory in more dimensions.
Wait, so by shrinking down, we learn about our own universe. How does that work?
It's all about perspective. Sometimes you need to simplify things to see the connections.
Okay, that's pretty mind-blowing. So we have these tiny strings, they're vibrating away. We can use this one-dimensional model to learn about gravity. But how do we go from this model to, the real
Ah,
universe?
that's where we introduce the world sheet.
A world sheet. I'm intrigued. Tell me more. A world sheet, huh? Okay, you've got to tell me more about this. It sounds kind of like a cosmic surfboard or something. What are we surfing on here?
It's more like, imagine a string moving through time. It traces out this two-dimensional surface. That's its world sheet.
Okay, so it's like a map of where the string goes.
Yeah, exactly. And it turns out the properties of these world sheets, like how they're shaped and how they interact, those properties have huge implications.
Okay, I'm hooked. Tell me more about these implications.
Well, remember how we talked about those infinities that pop up in other theories?
Right, like when you try to calculate something and it just breaks down.
Exactly. Those infinities, they often come from treating particles as points with no size. But in string theory, the strings have a length. They're not just points.
So instead of a tiny point, it's like a tiny piece of thread.
That's a good way to think about it. And because of that, because the strings have this inherent smoothness to them, it smooths out those infinities.
So it's like, imagine trying to cram an infinite amount of sand into a jar. It's just not going to work. But with string, you could just keep wrapping and wrapping, and it would be fine.
Exactly. The strings, with their length and smoothness, they might just be the key to avoiding those infinities altogether.
Wow, that's amazing. So does that mean that string theory could really unify quantum mechanics and general relativity?
Well, that's the big hope. But there's another even bigger, even more mind-blowing implication of string theory. It's about the nature of space-time itself.
Okay, space-time, now you're really going deep. What does string theory say about that?
It says that space-time might not be as fundamental as we think. It might actually emerge from the interactions of these strings.
Wait, so you're saying that space and time, the very fabric of reality, might just be like a side effect of something else?
It's like looking at a TV screen. You see a smooth picture, but really, it's just a bunch of pixels. Space-time might be the same way.
Wow, that is mind-blowing. So our everyday experience of space and time is just a kind of illusion. What does that even mean?
It means that if we want to truly understand the universe, we might need to go beyond our usual ideas of space and time. And string theory could be the key to doing that.
This is huge. But how does this emergent space-time idea actually help solve problems. What's the practical side of all of this? So we're talking about potentially rewriting the rules of reality itself. What kind of problems could this emergent spacetime idea solve?
Well, let's take the Big Bang as an example.
Okay.
Our current models, they kind of freak out when we try to go all the way back to the very beginning.
Right, everything gets squeezed into this infinitely tiny point.
Exactly. Infinite density, infinite temperature, those infinities pop up again.
Like a cosmic error message.
Exactly.
Yeah.
But if space-time itself emerges from something more fundamental, those infinities might not be real breakdowns in the universe. They might just be limitations of our current theories.
So it's not that the universe breaks, it's more like our models just can't handle it. Okay, that makes sense. What about other mysteries? Like, what about black holes? They seem to push our understanding of physics to the limit.
Absolutely. Black holes are another great example.
Yeah.
Regions of space-time where gravity is so strong that nothing, not even light, can escape.
Yeah.
But again, our current theories struggle to describe what's happening at the very center of a black hole, at the singularity.
Another cosmic error message.
Right. And this is where the idea of emergent space-time gets really interesting. If space-time emerges from the interactions of strings, then at the extreme energies and densities found inside a black hole, our usual notions of space and time might completely break down.
So instead of a point of infinite density, there's something else there. Something that string theory might be able to explain.
Exactly. It's like we've been trying to understand the ocean by just looking at a single wave. String theory offers a way to see the whole ocean, to understand the bigger picture.
This is all so fascinating, but you mentioned earlier that string theory is still a work in progress. What are some of the challenges that physicists are still working on?
One of the biggest challenges is figuring out how to test string theory experimentally. The energies involved are just way beyond anything we can create in our labs right now.
So for now, string theory remains a really compelling idea, a beautiful theory, but one that we haven't been able to fully verify.
That's right. But even though we can't directly test it yet, it's already had a huge impact on physics. It's pushing the boundaries of what we thought was possible.
It's like those early explorers who set sail into the unknown,
Mhm.
not knowing what they might find.
I like that analogy. Even if we don't find what we expect, the journey itself can lead to amazing discoveries.
That's a great way to put it. Well, we've journeyed from these tiny vibrating strings to the mind-blowing concept of emergent spacetime. It seems clear that string theory, even if it's not the final answer, has profoundly changed how we view the universe.
Absolutely.
And on that note, we'll leave you with this thought. If the universe is this grand symphony of strings, what other melodies are waiting to be discovered? What other secrets are hidden within those tiny, vibrating strands of energy?
That's something to think about.
Until next time, keep exploring and keep asking those big questions.